In this video, we will do inverse kinematics, and I'll illustrate this in a two-link manipulator. Inverse kinematics problem is a problem in which we're given the end effector position and we're asked to find the angles. Okay, in this case, if we have a two-link manipulator, the end effector is Q. And so the desired position of Q is given to us, and we are told to compute θ1 and θ2. We know that the position of Q is f of Q, that is a sum function of Q or θ1, θ2, and that is specified x-ray. In order to compute Q, we need to invert F, and then we would have Q. The issue, however, is that F is nonlinear, and so it is not possible to find an analytical solution to Q. And so we need to use some nonlinear method to compute Q. In this particular video, we will use the Jacobian, which I'll define next, to solve for the inverse kinematic solution. So what is the Jacobian? If you have a function f, which is composed of scalar functions, f1, f2, f3, so on, with q being the independent variables consisting of x1, x2, so on, then the Jacobian is defined as the partial derivative of f with respect to q. F in this case is size m cross 1, and q is of size n cross 1, then df dq will be of size m cross n. Okay, so coming back to this particular example, the position of q is given as rq equals f of q. If you want to compute the velocity of q, we take the derivative of q of r with respect to time, and that is dr dt, which is vq. That can be written as df dq times q dot, where df dq is Jacobian. So this expression is rewritten down here. We can cancel dt, and we are left with drq equals j delta q. The key equation is actually this equation. If we invert j, we can solve for dq. It is j inverse delta r. So what we do here is, in the numerical method I'll show you, delta rq is the difference between the reference minus the measured position of the end effector. So remember, the position would be x and y coordinates that is embedded here. J in this case would be 2 cross 2, so it'll be J inverse also will be 2 cross 2, and that will give us the correction in Q or correction in theta, which we then need to add to θ1 and θ2 in order to compute what is the change we need to do on θ1, θ2, so that Q can draw whatever curve we wanted to draw. In this case, we will use MuJoCo. We will look at two-link example. We would try to get the end effector to draw a circle. We will start the end effector at one of the along the x-axis, like it's shown over here, and then we'll get it to trace this curve. Example builds off the two-link manipulator I had done earlier. So I'm going to open that in the simulator. Okay, so the manipulator consists of two links. The gray sphere here is the end effector position, and this was modeled in this manipulator.xml file. Okay. I also wrote a py file, which basically moves this manipulator in some fashion. So if I run this, then the manipulator pretty much moves based on pre-specified angles, θ1 and θ2. Okay, so we'll start modifying this. In this case, we will first fix a particular angle, and then we'll look how the animation looks, and from there we will go for the inverse kinematics. So what I'm going to do is I'm going to pretty much delete this code, okay, and specify my own angles for θ1 and θ2. So I chose angles which work. θ1 is pi by 3, and θ2 is minus np dot pi by 2. These will be my initial angles, θ1, θ2. And if I want it to be played in a loop, just specify this θ1 and θ2. So I'm going to run this, and then you see that the manipulator is at a particular position. Okay, so this stays a little bit long. If you want to shorten the time, what I do here is I'll change this n to, let's say, 100. So the animation time will be short. Now here I don't quite have it at the exact location that's shown in the PDF, but it's okay. We can start from that position to draw the circle. Now what I'm going to do next is the following, which is, since this position is not exactly on the x-axis, it's somewhere here, I will first try to get the position of the end effector. To do that, I can access the end effector position right here by first running a forward step, so forward kinematics in this case, that passes the model and data. And then I can read off the position of, in this case, Q, which is the end effector, as data.site expose. So that site is specified in here. Okay, and since there's only one site, I can access that by passing on index 0. So if you want to see what it looks like, just to print position Q and run this. And it seems like it's printing something else in the loop. We can comment this out and rerun this again. So now it's just printing it once, which means it's printing this. So this is the position of the end effector. Okay, so what I'm going to do now is pretty much use this end effector position to specify the center. So if this is the end effect, if this is the start position, then the location of the center is going to be xc minus r, comma ye. So that's what I'm going to do now. So the center equals np dot array position q0, that's the x value, and minus r, which I need to specify what r is, and position q1, and let's choose r radius to be, let's say, 0.5. Okay, so this gives me the center. And now since I have the center and radius, all I'm going to do now is I'm going to specify my reference. The way I specify the reference is I'll define a variable phi, which wraps around the circle, so length space 0 times np dot phi n, and my x ref now is going to be center 0 plus r times np dot cosine phi, and my y ref is going to be center 1 plus r times np dot sine phi. And this basically gives me coordinates along the circumference of the circle, starting from the point I showed earlier in the notes. So now we have the reference. We can now start playing with the loop. What I need to do is the following. I need to get, so compute Jacobian J. I need to compute inverse Jacobian J inverse. I need to compute the correction. So dq will be J inverse times dx. And since I also need dx, I need to compute dx. And once I have computed dq, what I would do is update beta 1, beta 2. Okay, so let's see how these steps are done. So let's first compute the Jacobian. For that, I need to look at the API reference. This is the API reference. I search for mj underscore jack. This command will give me, or this function will give me the Jacobian. I need to pass the model data. Jack P is the Jacobian associated with the XYZ motion. Jack R is the Jacobian associated with the rotation of the end effector. We do not have to worry about this in this particular case because we are not looking at rotations. We need to pass the point. In this case, the point is the position of E, the end effector, and then we need to specify which body it is. Okay, so let's do all these things to copy this. And note that this is not Python code, but this is actually the C function, but we need to interpret it appropriately in Python. So let's put it here. Let's see how to go about doing this. So we say mj dot mj jack. We pass the model data. Then we have jack p. Then we do not quite need the Jacobian with respect to rotation, so we can pass none. We need to pass the position of E, and then we have to compute the body. Now, if you look at this, you can find the body number over here, or another way of doing it is to open, go to the simulator, drop the XML, say print model, then locate where the simulate.exe is, and that model will tell you the print model, which be mj model.txt, will tell you the body number for the last link. Now, in this case, it's kind of easy to compute that body number. The world body is always body 0. The first link is going to be body 1, and the second link is going to be body 2. So we need to put number 2 here. Okay, so now we have this. Before we do this, let's try to get what position of E is. So position of E, we actually did this step here. Position of, oh, sorry, I said Q. So let's call that position of Q. So I'm going to change this name to Q just to be consistent. So that's specified. The Jacobian is, remember that we're trying to compute the Jacobian of the end effector, which is going to have X, Y, Z coordinates. And that Jacobian is with respect to theta1 and theta2. So the size of P, we need to initialize this. So I'll say np dot zeros, 3, 2. Okay. So the 3 is for X, Y, Z, and the 2 is for theta1 and theta2. Okay. So we specified this jack P, position Q. Now let's see what it will give us. So print jack P, and note that this is going to run in a loop, so it'll keep printing this again, but for the same position. So it's printing, it stopped. So this is what it looks like, 3 cross 2. We'll have the same value here, and so on. So what we need to do here is we don't need the third row, and that's because we only interested in Jacobian of X, Y with respect to theta1, theta2, and we don't want the Z position. So what we'll do is we'll define J to be jack P, and we only take the 0th and first, that means the first 2 rows and all the columns. And so if you want to check this again, to print J, and then you can see it's 2, 2. Okay, now that we have got J, we can compute the inverse. The inverse is available in linalg. So it is J inverse equals np dot linalg dot inverse J. Yes, that'll give me J inverse. Then I need to compute dx. So dx is x ref minus x. Okay, so what's x ref? X ref is the reference position. This is something which I already specified here. I just need to pack that in an array. So I'll pack that as numpy np dot array position q 0, position q1, and x is my sorry, this should be my bad. This is actually the measured position, and this should be, the first one should be the x ref. So let's try this np dot array x ref def, and this should be index I. Let's see if this runs fine. Okay, it runs fine, didn't print anything, it's fine. Okay, now I can compute dq. dq is equal to j inverse dot ex. This is just doing the multiplication of a matrix times the vector. And now once we have dq, we do theta1 plus equals dq0 and theta2 plus equals dq. So we've updated it. Then it goes into, it updates in the data variable of MuJoCo, and then we do a forward step, increment time, and nothing needs to be changed here. So let's just run this. Okay, so it didn't look like it worked. We'll try to debug this. Okay. Let's perhaps, let's try to see if we can print something. So print the x. Let's not do this update because it gives me, it gives a problem. So it'll just keep moving. Let's try to print q. And let's see what's going on there. And also let's print j inverse. Okay, so if you see this, let's see. So we have, this is dq, looks pretty big. This is dx, this also looks big. And then we have j inverse. So nothing really looks wrong here. Let's see if we can understand if we did some errors somewhere in the code here. So position of q is correct, jack p, data all looks good. J inverse looks good. Xref is good. Okay, I think that this does not work the way it should work. So it should be dx equals np dot array xref minus position q0 and yref minus position q1. Okay, because this subtraction doesn't really work the way I do this. I've specified it. So let's see if this works. Okay, so I need to re-enable this update. Let's run this. Okay, that worked. Okay, so the error was in this part of the code. This is not the right way of computing the difference. So let me just delete this part. Okay, so now it looked like it did follow the circle, at least visually. So let's just try to actually take some data, save some data, and plot them. Let's comment this. So what I'm going to do is I'm going to specify a new variable called xall and yall, which is going to keep track of the position of q, the measured value. Maybe here I will do xall dot append. What I need to append here is position of q0. And then for y, I need to append q1. Okay. So once I've saved the data, I need to then plot it. So I'll invoke the, I wrote down some code earlier. There is nothing much in conceptually here, which just basically does the job of plotting x all versus y all, and then x ref versus y ref, each using different colors. So if they line up, then it'll be perfect tracking. I also need to import the matplotlib, so I'll do that here. Okay, and now let me run this. So it did the circle, and then it did this plot. which was shown on a different screen, but it all looks good. And here's the plot. Okay, so this is how you do inverse kinematics using the Jacobian.